So thank you very much. So I'm going to talk about duct-tape initial data. So this is an idea of improving your initial data for applied for boson stars, but should also be for other compact objects. So it's a neat. I hope this is a very neat little idea that maybe is very easy to implement. So that's what I hope that you take away there. So just to say very fast, I'm working with GeoJumbo. This is a numerical GR code with adaptive mesh refinement. It's fully open source, and I think its focus is where it's good at. It's very flexible. So we did things that were fairly exotic, like high dimensional black hole, cosmic strings, inflation. We also did black holes, of course, and recently we also studied dynamic friction of scalar fields. What I'm talking about now is boson stars. So Pedro already, I think, introduced this quite brilliantly before. I'll just give a second introduction in case. So an oscillaton or boson stars are fairly simple. You just have one scalar field equation. And so here you have the scalar field phi, and here x and y, the physical coordinates. And similar as you throw like a pebble in a pond, if you just let it run, it would just dissipate in a spherical wave outside, right? However, we are fully coupled to GR. So due to the self-gravity of these ones, we contain this wave. And so we have effectively a wave in a potential. It's very similar to what you probably saw in quantum mechanics. The wave in a box model that probably everyone studied. So, of course we can then split this up in the initial data. So we get gamma ij, k ij, phi and pi. I think these quantities I think has been already introduced. And so for single star, what happens here? So we're gonna look here at the energy density rho over this space. It's a slice through the boson star. And we measure the 5% size. So we look for the maximum energy density and go down to where it's only 5% of the maximum. And that is our size. Technically, they're infinitely extended. That's not very useful size, but this gives us an approximate size. So if I play this, the single star just sits there and oscillates. This is just what a single star does. This is his normal behavior. And so I want to kind of study binaries. So what I would typically do is I would superpose them like this. And again, I should say you cannot superpose in GR. That is, GR is nonlinear. So of course, but this will cause effectively some Hamiltonian constraint violation. However, if you could put them technically infinitely far apart, this would become, again, similar to the unit metric. They would just cancel, and you would retain the single star metric, and everything would be okay, actually. So you would be fine. So let's do this. And we also do this for all the other quantities, which they don't have any they go asymptotically to 0, so no problem. Let's see what happens. So I'm introduce now the action camera. So as the two boson stars are falling in, we're gonna put a frame around it, just follow it as it falls in and see what happens. And so this is the picture that we're gonna look at. You can see here. This is now the action camera. It's actually
5 minutes.
This is two boson stars, and we're just gonna follow one as it falls in. And so you can see the very high frequency oscillation, but you can see also now what is happening there. This looks like a longer, more wavelength oscillation. And the question was for us, and that caused us some very sleepless night, is this physical? Is this not? And after many stressful days, we found it's actually not. What is this one is actually, it's very similar to what happens if you squeeze a single star, right? Say we take a single star, we squeeze it a bit, and what will happen? So again, not anymore binary. This is a single star that we just squeezed by 0.1%, just barely. And you can see the behavior is very similar to what we just saw before, right? You have this high frequency oscillation, but you also have now this very long wavelength oscillation. And so what we kind of found is if you superpose in this specific way, where you just take away the identity metric, you're actually introducing excitations into the star. You are implicitly squeezing it. So how can you fix this now? And I was saying before, this is literally a 5-minute fix. So instead of using delta ij, you use hij. Hij is a well-chosen metric. What you choose? What you choose is effectively the second metric, gamma ij, 2, evaluated at the position of the first star. This might seem a bit convoluted, but it will be clear in a second. So if I evaluate the whole expression in the center of the first star, I should point out this only works for equal mass, this specific idea. You can see that this one actually cancels. So what we retain in the center of the star is the same metric as the single star. So kind of whatever squeezing has happened before, we kind of remove this now, or try to remove this by reconstructing a single metric star as good as possible. And we implemented this. And how does this look? This is again the action camera mute. This is the 2 boson star head-on merger, and with the fix now, with this new idea implemented, and it's gone. Whatever excitation you had before, it's completely gone. And at the end, you have some tidal deformation, but the impressive thing about this trick, it's just how easy it is, and it removes most of your problem. A nice side effect is also, it removes most of your Hamiltonian constraint equation. So you have an order of magnitude reduction in Hamiltonian constraint, which is just an indication that you're kind of doing the right thing. And I mean, and if you don't do this trick, there's lots of consequences. We found it distorts the gravitational waves that you get in the end. Sometimes it completely destroys your star in cases it should actually not collapse. So these excitations are fairly dramatic. But let me conclude very fast. This is an alternative to finding a proper initial data, right? This is duct tape. If your byte bursts, you can maybe just duct tape it over. It might be good for the next 5 years, but what you actually want, you want to call the plumber and actually fix your pipes properly. So again, this is very similar. This is a really good fix. It gets rid very fast of most of your problems, but it's not the proper thing. There's more work to be done to really
1 minute,
get this.
please conclude.
And now, another point, this is valid for equal mass, at least in this specific form. And the asymptotics are slightly changed, but these are the caveats. All right, I think that is my talk. Thank you very much. Any questions? I have 40 seconds.
Questions for Thomas, specifically?
So I have a question. Is that metric symmetric under exchange of star 1 and 2?
30 seconds.
Yeah, so this one works only for equal mass. So this is the drawback for this specific implementation. That's why it only works for equal mass.
Any more questions for Thomas? And thank you very much for a very interesting talk. The next speaker couldn't make it, unfortunately, so we have about a 9 minutes break. You can either, of course, now step out or use the time to ask questions to any of the speakers that spoke in this session and that couldn't really take questions. So it's a general floor. Ask any questions that you like of any of the speakers.
If we do have the time, because I was just writing a question to Thomas directly, but I can maybe also ask for everyone else, because this is like a really neat fix that you presented here, right? Could you also apply that to other types of stars, or in particular improve maybe neutron star initial data even?
Yeah. So I mean, again, I said this is the idea is just to reconstruct the single star metric as close as you can in the center of the star. And yeah, in theory, I have never tested it, but I would think it would improve to naive superposition, even for neutron stars. Maybe the idea for this one is it would be a good way of constructing a good initial guess for a proper solver. I think neutron stars have much better solvers already. So I'm not sure if that actually is an improvement there. But for boson stars, where we don't have this cool infrastructure, this is actually gets you somewhere. But maybe as a good initial guess, because even though when we try to solve the Hamiltonian constraint in a naive fix, we still had all of the problem. Even the Hamiltonian constraint was gone. You just kind of put in implicitly some excitations.
Okay, thank you.
Since boson stars were mentioned and the lack of good initial data solvers for that, and I see that Samuel Tootle is still around. Do you know how much work it would be to add something like a boson star initial data solver to your framework? So if I do something that's not a black hole, not a neutron star.
So you mean like writing a proper solver?
Yeah, because it's for example, it's a non-compact source. You might have to support either complex numbers or at least split them up into real and imaginary parts.
Yeah, so this one is this specific type of boson star is purely real. That's why it has these oscillations. There's, I think, there's other mini boson stars that Pedro mentioned, which don't have all of these problems. That there you have to split up in real and imaginary part. But yeah, I mean, writing these solvers is hard. Maybe at least we don't we're not super experts in it. So we tried a bit, but it seemed very hard for us just because we don't have much experience. Of course, probably if somebody who has more experience would, this is of course trivia. This takes me 5 minutes. That would be great. I would like to get in contact with you.
Okay, so the trouble is the math. It's not making it work in, say, GeoJumbo.
Yeah, no, I think, I don't even know what formulation to start with. So I just don't have the experience maybe to get how to do this. We thought of some ways, but we just don't know. We're not, yeah. Yeah, I mean, all of these ideas, this idea is relatively, it's completely code independent. This is, yeah. And I think that there's some really smart people thinking about this, I think.